Okay, hello everybody and welcome. Today's speaker is Ritwik Pal from IIIT Delhi, and his topic is on shifted convolution sum of Fourier coefficients of SL3Z Lecce mass forms. All
Yeah,
your
thank you, sir. Okay. So you want to finish? I just stopped you in between in the middle. Gaurav sir, you want to finish? I stopped
go
you in the
ahead.
middle.
All over to you.
Okay, thank you. Thank you. First, I would like to thank the organizers of this seminar series for giving me this opportunity to present this talk. So, so this is today's layout of this is the layout of today's presentation. First, we will talk about the modular forms and the SL3Z Hecke mass forms. Though the modular forms are not a topic of interest of today's presentation, but we'll still discuss it to set up the tone. Then we'll go back. Then we'll go to the shifted convolution sums, and we'll discuss its history and the motivation why people study shifted convolution sums. Then we will present our article on the shifted convolution sum for the SL3Z Hecke mass forms. So, just a second. So to define a modular form or a automorphic form, what one needs is a group which has a group with a group of matrices under multiplication, and something that is the group SL to Z, and H is the complex upper plane. So a holomorphic function from the complex upper plane to C is called a classical modular form of weight K, where K belongs to Z, if it satisfies two properties. First one is f of az plus b by cz plus d is equal to cz plus d whole to the power k times fz for every z in upper plane. And this property is called the property for modular transformation. The second one is it has to have the first one already induces that it will have a Fourier expansion, and the Fourier expansion will have positive coefficients as well have negative coefficients. But the second condition imposes that it only have the Fourier coefficients which has with the positive indices, and this is called the it vanishes at infinity. I vanishes at I infinity condition. So along with this condition, when if AF0 is 0, so the constant term is 0, then it is called a cast form. So attached to each cast form, or even every modular form, one can attach a Dirichlet series, which is given by LFS is equal to lambda fn by n to the power s n greater than 1 for real s greater than 1. And for cast form, this can be analytically continued to the whole complex plane. Now we come to the mass forms. So a mass form is not a holomorphic, is not necessarily holomorphic. In fact, it is a smooth function from the complex upper plane to C, and it satisfies four properties. First one is the property for the same property for the modular transformation. Second one is that it will be an eigenform for the hyperbolic Laplacian operator. And here lambda is the eigenvalue of the Laplacian operator, hyperbolic Laplacian operator. Third, it has to satisfy some growth condition with respect to y, where this z is represented by x plus iy. And fourth, it is that from 0 to 1, f of z plus t dt will be 0. So if a form satisfies all those four conditions, this is called a mass form. So mass form has a Fourier expansion. It's real analytic. So there is a root over of y, cn, k mu of 2 pi n mod n y is basically a Bessel function of second kind. It will be 2 pi n.
And so many
And
people.
this n not is equal to 0. I am only giving.
Ritwik, please go ahead.
Hello.
Yeah.
Okay.
There was some disturbance from somewhere else. Yeah, let me go ahead.
Okay. So Knu is the Bessel function of second kind, and this Fourier expansion is given over n not is equal to 0 and n belongs to z. So both the positive and negative indices are covered. So it has a Dirichlet series attached to it, and the Dirichlet series converges for real s greater than 3 by 2, and it can be analytically continued to the whole complex plane. And this is for cast form only. I am not going to the Eisenstein part. So when it comes to GL3, or in our case, the SL3Z cast form, first thing is that there is no holomorphic analog for GL3. The reason is algebraic. So even we won't go into the definition of the SL3Z SL3Z cast forms. We are just giving its Fourier expansion. So rather than an exact Fourier expansion, it has something called the Whittaker Fourier expansion. Let us just focus on this M sum. So first WJ is called the Whittaker-Jacqua function, and it depends on four different indices. And this Fourier-Jacobi coefficients, Fourier-Whittaker coefficients, not Fourier-Jacobi, sorry. Fourier-Whittaker coefficients is given by AMN, and is M runs from 1 to infinity, and N runs through whole Z, but N not is equal to Z. And its L function, called the Goldman-Jacqua L function, is given by A1 N by N to the power S, N from 1 to infinity, for real s greater than 1, and this can also be analytically continued for the whole complex, to the whole complex. Now, this space of cast forms for SL2Z, for the modular forms or the SL3Z Hecke mass forms. So this space of cast forms has a special basis. So this basis is called the Hecke basis, and each elements of this basis are the simultaneous eigenvectors of a sequence of linear operators called the Hecke operators. And this sequence of linear operators is given by Tn, and lambda Fn is basically its eigenvalues, Hecke eigenvalues. So first of all, the Hecke operators, just one thing, let me be clear, that Hecke operators for the SL2Z and SL3Z are different, but they are defined quite analogous. And lambda Fn is the Hecke eigenvalues, and in these cases, they are basically a linear multiple of the Fourier coefficient. So when F is a Hecke eigenform, then we can write its Dirichlet series as a L function. So here I have given the L function only for the SL3Z for degree 3. For modular forms, it will be a degree 2. And this L function, so basically there is an Euler product of degree 3. So for SL3Z, naturally, the L function is a degree 3 L function. So however, till now, whatever we have discussed, we don't need that much of theory in our presentation, or in our article. We did not need it. So we needed only 3 properties of this ANN. So first one is this Rankine-Selberg estimate, where basically M square n up to n, capital N, AMN square, this mod square, is bounded by n to the power 1 plus epsilon. This is called the Rankine-Selberg estimate. Second one is kind of a Hecke relation, where this AMN is given by this, AMN is D divided D is the GCD of M and N. D divides M and N, not GCD. And so AMN given by D divides, D goes through the divisors of the GCD of M and N. And it is mu D, A of M by D, comma 1, A of 1, comma N by D. And third one, we need the Voronoi summation formula. So the Voronoi summation formula, we do not state it here. We will state it when we use it later in the presentation. Now we come to the definition of shifted convolution sums. Let alpha and beta be 2 sequences. Then a shifted convolution sum is basically sum over the sequences alpha n and beta n, where n truncated up capital N, such that a linear multiple of n and a linear multiple of n has the difference h. This h is called the shift of this convolution sum, and that's why this basically named after. That's why it's called a shifted convolution sum. So in many cases, this n, a, and b are kind of superficial. Superficial means that if one takes a and b is equal to 1, and one can work with it, and then sometimes not always, one can also work with, if one can work with A is equal to 1, and then one can also work with arbitrary A and B. So for this uh, 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 kind of will mostly be asymptotic. In case the asymptotic is not possible, then we want to get a very good upper bound, at least a non-trivial upper bound. And once we get a non-trivial upper bound, we want to get a much sharper upper bound. So why do we study the shifted convolution sums? So when these coefficients are when these arithmetic functions come from the Fourier coefficients of L functions, automorphic L functions, then this is related to quantum chaos. In fact, this is related to this as so having a non-trivial estimate for the shifted convolution sums will have implication on the quantum unique ergodicity conjectures, QUE in short, and it is due to an 2001 article by Peter Sarnak. Second, it appears in the moments of L function, especially after writing this L function into an after we write the L function in terms of approximate L function. So in the approximate once the approximate L function is function equation is approximate function is applied, then it appears in some non-diagonal terms, and it appears naturally. That's why the non-trivial estimate for the shifted convolution sums are used in many cases. In fact, the non-trivial estimate for the shifted convolution sums is useful for the for DN for the divisor. We'll come to that. For the divisor functions, it is related to the moment estimate for the Riemann zeta function. And because it is also related to, because moments and the subconvexity are kind of related, so it is also useful for the study of subconvexity of L functions. So subconvexity is basically L functions. So attached to L function, one can attach a certain quantity called the analytic conductor, where QFS is the analytic conductor. So the trivial bound is QFS to the power 1/4 plus epsilon. And if one can improve that bound 1/4, that is the trivial one. So 1/4 plus epsilon, one can improve it by a little delta, then that is called the saving of the subconvexity. And these shifted convolution sums appear also in the in certain non-diagonal terms when we want to estimate the subconvexity estimate for the function. Now let us see some classical problems. The twin prime conjecture for P, and so it says that P and P plus 2 is prime for infinitely many primes. P and P plus 2 are both primes for infinitely many primes. So this twin prime conjecture implies that, or even this von Mangold, this shifted convolution sum with respect to the von Mangold function implies the twin prime conjecture, and both implies the other. First of all, yeah, I want to mention that I have written it here. It's not a theorem; it's a conjecture. It has not been proven. So Chaulas conjecture involves the Mobius function. So it's asked that mu n into mu n plus 1 is small o of n. Even any non-trivial estimate, it is not known. And any non-trivial, I mean, basically, if Chaulas conjecture is proved, then it will also imply many other conjectures related to the distribution of primes. And third one, we come to the divisor correlation conjecture. So dkn, I am defining it as the number of ways one can write n as product of k number of positive integers. So dkn is basically writing n is equal to n1, n2, dot in k. So total k number of positive integers, and the summation is over 1. So the divisor correlation conjecture is a dkn and bl n plus h is some polynomial over log n, which depends on k, l, and h times n plus big of n to the power half plus epsilon. So among these three conjectures, the third one is the most active, and a lot of people work in it, but no one has been able to prove this conjecture. However, there are some average estimate for the divisor correlation conjecture, and I think also it is there for the von Mangold function also. So there are a lot of, and because this is a quite an active area, it's an active theme of research in analytic number theory. So there are a lot of articles, there are a lot of papers. We only want to list only a few, which will be relevant to the latter part of the presentation. So the first result for the shifted convolution sum is due to Ingham, where dn is the divisor function. So the Ingham to show that this dn into dn plus h is some constant times n log square n plus big O of n times log n. So it was Ingham did it in 1927. So later, Easterman showed that this he improved the main term. He showed that the main term has a term like a1 times n log n, and he improved the error term also. He showed that the error term is n to the power 11 by 12 plus epsilon. Now, almost 50 years after Easterman did it, Desulier and Ivanich, they connected this dn plus h with the with certain sum over the Klusterman sums, and this certain sum of the Klusterman sums was related to the Kuznetsov trace formula of the automorphic forms, and there he was able to improve the error term, and he showed that the error term is big O of n to the power 2 by 3 plus epsilon. Now, many authors considered when taking dkn instead of dn, many authors considered that sum also, including authors like Fully, Linick, Motohashi. But the best estimate is due to Motohashi, and Motohashi showed that for this dkn dn plus h, he was able to show an main term, and he showed that the error term is big O of n by log n times log n to the power sum. Now, for SL2Z holomorphic uniforms, it was first Anton Wood who showed that there is a cancellation over the shifted convolution sum, and he was able to save the trivial bound is n, because one can do in Cauchy, one can apply Cauchy-Schwarz and then apply Rankin-Selberg estimate, and one can see that the trivial bound of the shifted convolution sum is n. So Good was able to save n to the power 1 by 3 minus epsilon. Yeah. In the same article, he also showed that average, if one takes an average over the seat and h up to n to the power half, one can get more cancellation. So basically, this sum of this total length of the sum is n to the power 3 by 2, and he was able to save n to the power half. For the mass forms, it was for Jutila who showed that this shifted convolution sum lambda fn into lambda n plus h is basically bounded by n to the power 2 by 3 plus epsilon. This is for SL2Z mass forms. Okay, for h, when h is quite a little big, it's showing the shifted convolution, showing the cancellation is a little bit more easier than when h is small. So mass achieves the harder part. And all these results apply the spectral theory of automorphic forms. So, frankly speaking, the shifted convolution sum of automorphic forms either take one of the two different routes. Either it takes the spectral theory route or spectral theory of automorphic forms, or it takes the circle method route. There are various circle methods. So or it takes the circle method routes, or recently it takes the delta method route approach, which is basically an alternative of the circle method. It's kind of a circle method, but not exactly. Yeah, it's an alternative of the circle methods, and it is due to Duke, Friedlander, and Ivanich, DFI. And also, this delta method approach, one uses it with the innovations made by Munshi, Ritomoto Munshi, with this DFI delta method. So with their landmark delta method, so DFI, Duke, Friedlander, and Ivanich, they first get a non-trivial estimate for this shifted convolution sum. So lambda f of an, lambda f of bn. That they also need an extra smooth sum. So smooth sum which satisfies some decay condition with respect to its partial derivative. So smooth sum is needed because because of some analytic terms, certain analytic risk will come, and the smooth sum basically simplifies that estimate, simplifies the ways of calculation. So from smooth sum, one can also remove the smooth sum, but yeah. So but with a little bit, what shall I say? With a little bit worse estimate. But yeah, taking a smooth sum is not a big problem. So here also, yeah, first thing you may note that I didn't give the right hand. So what is the exact for the exact saving they have got? So this is because the right hand side is quite complicated. So I did not. I just refrained from writing it out. So building upon this DFI delta method, Parchos made and further improvement over this estimate, and we also use in our presentation that this DFI delta method, obviously with the innovations made by Moons. So this is for GL2 cross GL2 shifted convolution sums. Now considering the GL3 cross GL2 shifted convolution sums, so Pete first considered D3 n plus 1 lambda Fn and n up to capital N, and he was able to save n to the power 1 by 17. So Moonsey later, he considered this shifted convolution sum where he replaces this D3 by the Fourier coefficients of the automorphical function. And he was able to save n to the power 1 by 26. And Moonsey's, so there are further improvements over the results of Moonsey, but they all built upon the Moonsey's paper, Moonsey's theme, and they do some optimization. Now, when it comes to the shifted convolution sum for the GL3 cross GL3L function, it has been quite a challenging task to get a cancellation with only one shift. So what one considers an extra average over the shift. So here, this pi1 and pi2 are two different GL3 forms, and so n up to x and h up to capital H. So the idea is to get an non-trivial estimate for this shifted convolution sum, so that this range of h is as big as possible compared to the here there's a typo. I should have written this x. I should have written n instead of x in the shifted convolution sum. So the aim is to get a cancellation for the shifted convolution sum with such that the range of h is as big as possible compared to n. And it is usually what happens is that when h is a little bigger compared to n, then for example, when h is bigger than n to the power half, it is relatively easier to get a cancellation. So the challenge appears when h is less than n to the power half. So first, it was due to Bayer, Browning, Marasinga, and Zhao. They took the shifted convolution sum for D3n plus h, and they have a main term m of. I'm writing it here as m of n comma h. I will say about it a little later. And they was able to show that this shifted convolution sum minus this term mn h is bounded by this expression on the right hand side, and this one can check that this right hand side is non-trivial for the range h is bigger than n to the power 1 by 6. Now this main term, we were able to show that this mnh is a main term only in the case n to the power 1/3 plus epsilon, but beyond n to the power 1/3 plus epsilon, that means when h is less than n to the power 1/3 plus epsilon, you are not able to show in their article that this is a main term. But the conjecture is that this should be the main term. Okay? However, the error term is non-trivial for h up to n to the power 1 by 6. So when one replaces this the D3n with the Fourier coefficients of the SLCZ HKMAS forms, it was first considered by Singh and Harun, and they were able to show that a non-trivial cancellation for h up to n to the power h greater than n to the power half plus epsilon. Yeah, half plus delta or half plus epsilon, yeah, whatever we can say. The trivial bound for this one may note that this trivial bound for this shifted convolution sum is nh to the power 1 plus epsilon. And that for trivial bound, one can first apply to the Cauchy and then apply the Rankin-Selberg estimate. In their landmark paper, Dasgupta, Liang, and Young, they showed that the shifted convolution sum is bounded by this quantity, and this is non-trivial for the range when capital H is 10 to the power 1 by 4 plus epsilon. And why I'm saying this is non-trivial? Because this shifted convolution sum is implied that is bound for the shifted convolution sum implied that the second moment of the GL3 SL3 the second moment of the GL3L function is the base bound for the second moment. The second moment they got t to the power 4 by 3 plus epsilon, and the trivial bound is t to the power 3 by 2. And it is quite a good bound. So the second moment of the GL3L function can be compared to sixth moment of the Riemann zeta function. So we improved. With my co-author Sampurna Pal, we improved their result for the range of H. So we got a non-trivial estimate for a higher range of H, and this right hand side is non-trivial for the range H bigger than 10 to the power 1 by 6 plus epsilon. So now we come to the brief sketch of the proof. Our method is, we have said that our method is basically the delta method of deep Friedlander Riemann with the innovations of the Munsi, with innovations by Munsi. So this is the first. So the first setup is only the delta method. The latter, to a certain stage, of course, the problem completely diverges. So so delta n is given by Kronecker delta. So delta n is given by when n is equal to 0, this is delta n is 1, and when n not equal to 0, delta n is 0. So in this A1n plus h, if we apply the delta method, we write delta of m minus n minus h because we want to separate, we want to detect m is equal to n plus h, right? So if we introduce the delta method, when we introduce the delta, so and automatically an extra sum over m appears, and this shifted convolution sum takes this structure. Now delta has an expansion. This current expansion is due to Munsi. I have written it in a more simpler form than it is there. So I will explain what is there. So there is a big parameter C. C is our choice. We can choose C later. Then there is a sum over Q up to C. Then there is a sum over A modulo Q, and the summation is taken over the summation is taken over the co-primes modulo Q. So there is an exponential twist e to the power an by Q, and then there is this integral GQ base e to the power nx by small q times Q. Oh, this capital Q inside the exponential, inside the integral will be actually C. I have written it mistakenly, capital Q. Sorry. And this, we don't need to know much information about GQX, what exactly GQX is. We just need to know that GQX is small when x is small, and it has a its partial derivatives as a decay. And the integral is basically subordinate minus e to the power epsilon plus e to the power epsilon. So after we apply the delta method, first what we do is that basically we split this Q sum. So when we apply the delta, when delta of m minus h will appear, so this we split this Q sum into dyadic ranges. So dyadic range just basically helps the calculation a little bit. It's not necessary, but it simplifies the computation of the disposition with only respect to some. The trade-off is basically some log of C. We have taken C to the power epsilon. So basically our SQs take this structure. So there will be this integral, there will be this 1 by C, 1 by Q. Yeah, those things will be there. Essentially, the most important part is that, so this under this A mod Q, and when A is co-prime with respect to Q, there is a sum over H, there is a sum over n, and there is a sum over n. So this m and n sum involves the Fourier coefficients, and the h sum does not involve the Fourier coefficients. There are only arithmetic sums. So first we apply the Poisson summation formula on the h sum, and we get an asymptotic. So this Poisson summation formula is basically assuming that s is a function which is L2 square integrable, and also further assume that s has a sufficient decay after beyond the compact. S has a compact level. Take it as S as a compact level. Yeah, probably we want to take some decay condition, then it is sufficient enough. Then summation of s of n is basically summation of n up to z. Fourier transform of this s hat is basically Fourier transform. So Fourier transform of s of n. So this is the Poisson summation. And we apply the Voronoi summation formula on the n sum and h sum. So let me explain this a little bit. So the right hand side, what you see on the right hand side of this, or the second line of where my cursor is there, is n to the power 2 by 3. There is a sum over m1, there is a sum over m2, there is a Kloosterman sum, and there is im. So this is not exactly the Voronoi summation formula. This is the transformed the Voronoi summation formula after a few transforms of the right hand side. And because this seminar also involves special functions, so in Voronoi summation formula involves the Bessel functions of the second kind, also the modified Bessel functions of the second kind. And for transformation of this of the right hand side, one needs the property of the Voronoi. One needs to use the property of the Bessel functions. So in the right hand side, there is this integral im. So this im is given here. So after applying the Voronoi summation formula, my S takes more or less a structure like this. The noticeable part is that basically it has an integral from minus infinity to plus infinity, or basically this minus infinity to plus infinity, it should be minus e to the power epsilon to plus e to the power epsilon, because GQS is very small up to a certain stage. And there is Sm and Sn. So this Sm and Sn, because this involves this integral im and in. So essentially, this leads to one has to estimate this particular integral. So there is this triple integral over x, y, and z. So at this stage, we choose our c. So this choosing c, we choose a c is equal to root over n by k. Now, this usually what happens is that if we choose c is equal to root over of n, this usually gives kind of the trivial estimate. So introducing this extra parameter k in c, and so that this k appears inside this exponential, is basically due to the conductor lowering mechanism of Muncy. This introduces an extra analytic twist inside the summation, and that results in a saving. That results in a saving with respect to k. And this conductor lowering mechanism of Muncy has many avatars. This is one of it. So now, basically, if we apply this and we apply the stationary phase analysis of the triple integral, and it leads us to estimate an integral like this. So here the noticeable part is inside this exponential, the phase function involves the square root of n1 square minus n2 minus square root of m1 square minus m2. Now, from here, if we apply a stationary phase time method, we won't be able to get a good cancellation better than what Dasgupta and Liang achieved. So what we do is basically we change that phase function into a phase function which is linear over the size of n1 square n2. Here you can notice that this is square root of n1 square n2, and here we have showed that the phase function has changed to linear over n1 square n and m1 square n2. And this is basically the, if if one consider the size of n1 square n2 and n1 square n2, so this is linear over that size. This part was this transformation of the phase function was the was one of the main novelty of our article, and this essentially helped us to get an extra cancellation of the size of root over of k, that k we introduced, k parameter that we introduced, root over of it helps us to get a cancellation of the size root over of k. And so this so one of the key input for this transformation of the phase function was the Mellin-Barnes integral representation, integral formula, Mellin-Barnes integral formula. And it's quite, the proof is a little bit complicated to discuss here. So after we convert this this integral, we convert the phase function. So basically, the crucial part in the S is to estimate this kind of sum. Now here you note that, here let us note that there is a sum over Q outside, there is a sum over H. Inside there is the absolute square, and inside the absolute square there is a sum over M. Basically, this in this position, one applies the large-sig duality principle. So what large-sig duality does is basically there is a sum over n, and there is an absolute square, and inside the absolute square there is a sum over n. Now, what large-sig duality does, it makes it upper bounds that quantity expression by another sum, where the sum over n goes inside and the sum over m goes outside. And at this stage, one should not apply and trivial bound. So rather, one should open up the square to get a further cancellation or further optimization. One should open up the square after applying the large-sig duality. So we apply the large-sig duality, and after applying the large-sig duality, yeah, there are many other terms, but one of the key terms is basically this delta. And delta, you have a sum over Q1 H1. Basically, after opening up this, after applying the large-sig duality and opening up this absolute square, you have a sum over Q1 H1. You have a sum over Q2 H2. Along with there is an there is a Kusterman sum twisted with exponentials, this Tm. And so this estimation of Tm was quite a challenge. And we estimate Tm. It involves a lot of character sums. We estimate the Tm and put this back to delta. And then we apply the Cauchy-Schwarz inequality on delta. Now, the way we apply the Cauchy-Schwarz inequality is basically we take everything out. There is this sum over Q1 is there, and there is sum over Q2. So these two terms S0 and S1, they will have one of them will have Q1 term, and one of them will have Q2 term. So in the Q1 term, that is the S0, we apply it, we estimate it trivially. In S1, we rather than estimating it trivially, we open up the square again. So there is, yeah, so this open up the square over this absolute square over Q2. When we open up this absolute square over Q2, I think probably, I don't know, you can, let me, yeah. What happened? Yeah, so there is an SQ after alpha 3. I don't know if you can see it or not. So this SQ is basically this character sum over the additive characters. So in SQ, first we apply the so basically Q2 is equal to Q3. This Q2 is equal to Q3 is much yeah. It results in a much. So when Q2 is equal to Q3, there's this one of this Q2 sum and Q3 sum in S1 is actually collapses. So it gives us setting. So the generic part is when Q2 not equal to Q3, and we apply the Poisson summation formula for the S1, and we estimate the this character sum, and it gives the bound S1 up S1 given by this right hand side. Now at this stage, if we write k is equal to n to the power 5 by 9 by if we take k is equal to n to the power 5 by 9 by h to the power 10 by 9, we get the original shifted convolution sum S dash is bounded by this right hand side. And this already give us this is already non-trivial for h greater than n to the power 1 by 5. Recall that this Dasgupta, we have already improved over the range of Dasgupta-Liang, which where the non-trivial saving for h bigger than e to the power 1 by 4. However, we did not end it here. Again, we apply uh, and trick by Munshi, Agarwal, Liang, and Munshi, and they call that trick Cauchy-Schwarz ad infinitum, and I will also call it that. So what one does, yeah, one can notice that. So when one applies a Poisson summation over the SQ, and rather than estimating it trivially, there is a new variable of the so this dual variable of the Poisson gives a new variable. So this new variable, let me open this, open all the slides. So this, in this new variable, you can see that in any Sj j minus 1, so you have basically q plus j number of yeah, there are j plus 1 number of q's, and along with that there is this coefficient alpha. So what one does is this, in this j minus 1, one applies the Cauchy. So in Cauchy, all the this up to qj, up to qj minus 1, everything stays outside. Inside one, in this one term, it will be qj to the power alpha. This alpha j to the power for one term one takes alpha j square summation over qj, and for the another term, so this automatically this alpha j plus 1 will be there. Now we estimate this first term trivially. In the second term where this alpha j plus 1 is there, we open up the absolute square. After applying the absolute square, again another sum like this SQ will appear. Sorry, another character sum like this SQ will appear. And when we, after this SQ, we again apply Poisson on SQ. So there will be a new variable. There will be a new variable of the dual variable due to this Poisson, and we apply the same trick again and again, and repeat it iteratively ad infinitum, infinitely many times. And after doing this, if we plug everything back into our S dash, that is the shifted convolution sum, we will get our result. Thank you.
Okay, thank you very much. Any questions for the speaker? Questions or comments?
Sir, just one question I have. I wanted to ask, am I audible?
Yeah, you are audible.
So
Aviral.
what was, yeah, Aviral, yeah. So what was that V function that you said that it can smooth the sum or something, right?
Function?
The V function that was in your summation.
Yeah. The smooth function. Yes.
So how does it help you?
Exactly. Yeah. So basically, when we apply the delta method, so V function has some. So this V function has additional conditions. So this additional conditions is, first of all, you have a compact support, and you have a decay. So this decay of V function, when it appears in this integral, this decay of V function kind of rather than this sort of integrals. I'm giving just one example. This integral is over from 0 to infinity. Rather, this basically truncates the integral after a certain stage. So integral is majorly truncated by this V function, and you can see this same V function, the same idea of this V function when what you get in when you apply the approximate functional equation.
Oh, okay.
So it will be clear only if you do the calculation. So V function comes with additional conditions, like it has a decay, you can see that V has a smooth function supported in, it has a compact support, and it satisfies some decay condition. So J is the J derivative, okay, not power J. So
Okay.
when you apply the integration by parts, and you apply integration by parts repetitively, you can estimate those integrals. Yeah.
Okay, because of this decay condition, right?
Because of the decay condition, right?
And can you please show that Voronoi summation formula once again?
Yeah, that
So this
I
is
was
not
also
exactly
thinking of this.
Voronoi. This is not exactly Voronoi. So there are other terms. This I before that this is not a Voronoi. So there are other terms which involves the Bessel functions of the second character.
Okay, okay. Thank you, sir. Thank you for the nice talk.
You can get this Voronoi summation formula. You can get the Voronoi summation formula. It's even in our article. It is there. Yeah, in our article you can see.
Okay. Thank you, sir.
Thank you. Any other questions?
Okay, we did not yet archive our article. It has, although it has been sent for publication. You can see it in the paper of Agarwal. Agarwal Liang Munsi. You can see it, or you can see it in the paper by Dasgupta Liang Yang. You can see the paper by Dasgupta Liang. What they mentioned Dasgupta Liang Yang. Yeah, Dasgupta Liang Yang.
Okay.
Okay, thank you. Any other queries or comments? Okay, if not, let us thank the speaker once.
Just I want to mention.
Yeah.
Whoever asked about the Voronoi summation formula. So the Voronoi summation formula, I should mention this here. So this Voronoi summation formula for GL2 and GL3 is a bit different. Okay. So if you are applying the Voronoi summation, this is here what I have written is the Voronoi summation formula for the GL3L functions. Okay. For GL2, it's a bit different, and there are few here and there different versions of GL. I mean, just with one is the another modification of other. One is the modification of another. Basically, there are few different versions of this GL2 Voronoi summation formula. For GL3, this is done by Miller-Smith and Goldfriend-Lee. And this Miller-Smith also gives the recipe for the Voronoi summation formula for arbitrary GLN. And for arbitrary GLN, there are basically box of n by 2 number of Voronoi summation formulas. So if you are looking for GL2 Voronoi summation formulas, it's a bit different from what is given here. Even the transformations will be a bit different. It's a little less complicated.
So is there a standard reference for this, or you're just using it?
I think probably you can. No, I actually, because I work with this, so I know it. Standard reference where I can see. You can see the Voronoi GL2 Voronoi. Yeah, there is a small template by Miller which is available which will be available in the internet.
Oh, all right. Thank you.
Right Voronoi summation formula. Then.
Okay. I guess if anybody has a query, they can send you email or something.
Yeah, sure, certainly.
All right. So let us thank the speaker, please. So let me stop.